All right, the recording has started, so whenever you're ready.
Okay, sounds good. So good afternoon, everyone. My name is Major Sean Clement. I'm with TRAC Monterey out here in Monterey, California. I'm going to be talking to you a little bit about our project. This is a multi-year project enabling automatic course of action development for combat simulations, or SIMS or AI for combat sims, as we call it for short. So, like I said, this is a multi-year project in which we've been building iteratively on previous results. We started out with literature review and problem understanding. There's been a lot of work that's been done publicly in this arena, but a lot of it is done in very well-defined games. So chess is a extremely well-defined game. Go is a well-defined game in that there are really well-known rules. And then even within StarCraft, the DeepMind project, which was extremely impressive, there's known rules and there's known effects for every piece and part of that in there. And so what makes this different is we're trying to push this into a regime where maybe all of the rules aren't really known, or if we have different effects that occur on the battlefield, that those may not be strictly well-defined, or they may be distributional. And so that makes it fairly challenging. But in order to get down that road, we have to build a proof of principle, proof of concept. And so that's really what we've been working on with different agent architectures and different environments. And right now we're using the OpenAI environment, and we're using a TRAC-created tool called the Versatile Assessment and Simulations Tool, or VAST engine. It is primarily used for wargaming. And our hope is that once we get far enough into this project, that we can decrease the amount of personnel hours it takes to run a war game, because if we can automate part or all of one side of a war game, we drastically reduce the amount of planning that's involved. We can go through and start changing the different technologies that we can give to that agent in that war game, and then do some training runs while maybe the weekend before a war game occurs, and then it's all trained up. So the progress we've had to date so far, we've really looked at a first principles approach to this particular problem. So what that means is that we are looking to teach an agent the principles of war, not necessarily specific tactics. So the first thing we wanted to have them learn was objective, and that's really sense where the enemy is, move towards the enemy, attack, and learn. And then after that, we're looking at mass and economy of force. So mass and economy of force, for those of you who don't have a military background, they're kind of opposing fundamental aspects of war. So mass is that you want to take all of your fires, all of your different kinetic effects, and get them all on the same point to produce the desired outcome. Whereas economy of force is that you only want to use enough force to obtain the objective you want, and you want to leave some stuff on reserves. The purpose of that is to give yourself some operational flexibility or some tactical flexibility there. And in case there's more enemies out there that you didn't know about, or if the situation on the battlefield changes, you're not completely locked into one course of action. This year we've integrated with VAST, so we're able to pull in the trained agents into that versatile assessment and simulations tool, and we are in the process of going through some training runs with larger scenarios, also implemented key terrain, some terrain restrictions that inhibit movement, and seeing how the agents deal with these types of problems. Our next steps, as we go to these larger scenarios, we're looking at different unit types. So we're really getting into, can the agent understand and employ indirect fires, so things like artillery that can shoot over the horizon or that you don't have direct line of sight on, expanding the scale of the scenario, like I said, and then putting in even more terrain effects. We've done some experimentation, but at this point we're talking about large-scale experiments. So can we put in marshy terrain, perhaps that only infantry units can move through, that armor units would have a great amount of difficulty moving through, or it might be impossible for them to move through, or effects of urban terrain, things of this nature. So right now, what we do to train the agent is we start off in the OpenAI Stable Baselines toolkit, and we have developed effectively a mini wargame engine within the OpenAI framework. And we give the agent a curriculum that it needs to learn from. And you can see the objectives that we have there in blue are ones that are done, or ones we've seen optimal behavior demonstrated. Black is still yet to be trained. Some of these we've worked on, some of them we haven't yet. So we select the curriculum that we want to see. We put the agent through that curriculum, and there's a lot of individual choices that really affect everything to do with this process, right? What curriculum you choose matters. What network architecture, not even the hyperparameters, but the architecture itself matters. Then, the hyperparameter tuning is obviously very important. Learning rates are extremely important. Do we modify the environment so that the agent is learning the true behavior, or are they only learning something that we're not thinking of? So a really good example of this happened in our first year, where we were training the agent to go towards and engage the enemy. In our first year thesis student was working on this. Well, if you rotated the battlefield at all, the agent would still just proceed north, because it didn't learn go towards the enemy. It learned go north because the enemy is always north. And so we have to be really careful. That's an overly simplified example that came from our very first year working on it. But those types of lessons occur regularly within reinforcement learning, where you have to be very careful that you're teaching what you think you're teaching, and you're not teaching, some secondary or tertiary effect of just how you've set up the board for the agent to play. So that becomes really important when we start talking about, what the war game view is versus what the state view is there, that you can see in the bottom right. And then tuning the agent. So we go through and we observe the agent's actions, and then we can adjust different reward signals or parameters to see different behaviors that we'd want. So last year we found that if you adjusted the time discount factor, that was really the big difference between seeing mass versus seeing economy of force. If you told the agent that it's imperative that you defeat the enemy quickly, it used mass every single time. You left absolutely nothing in reserve, and it would send every unit you gave it towards one enemy and then all towards the next enemy, because that's what it learned was important. But if we started to dial down that reward for being very fast, we would see that it would start to leave itself some flexibility, and so it would leave a unit behind and pull security, for lack of a better term. And then once we have that tuned agent, and we go through this iterative cycle a few times and through a lot of experimentation, we can then take that agent, move it over into the VAST framework, and then we can see that agent working within the wargaming architecture. And that's exciting because we're hopeful that means that we can take one of these trained agents, put it into VAST, and then we can get to a point where we can start giving a human player a worthy adversary on the other side. So when we start talking about offense and coordinated maneuver, we're talking about sensing the enemy, moving to that location, attacking the unit, etc. So here are some sample engagements where we see the blue units move towards the red unit. And so that's just a very quick demo. This is our trained agent, and we move this red agent laterally back and forth just to make sure that it's, again, not only learning to move down, but it's not moving, it's not learning go to the bottom left corner every single time. So those types of things are important. But we see here some small massing effects as we have 2-on-1. So objective seizing key terrain. So in this particular example, the gray terrain represents key terrain. So you can win the scenario by either defeating all the enemies or holding the key terrain. And so as the blue units go forward, they can destroy the enemy and seize that key terrain, or they can move towards the gray after they've destroyed the enemy if it's not on there, or they can just go to the key terrain and then secure it. And so you can see kind of all of those different scenarios play out, where the blue engages the red that's on the key terrain and then occupies it, or it destroys the red en route to occupying the key terrain, or if it doesn't need to destroy the red, it just occupies the key terrain and then sets up a defense. And so that's all very promising. And our next example here, this is what I mean by economy of force. With economy of force, what you're going to see is that the blue units should split up into two groups, because you have a weakened red enemy in the bottom right there. So you should have one unit go after that weakened enemy, and then 2-on-1 against the stronger enemy if we see proper economy of force. And so that's what we see here out of blue. dive in between the two red units, split them in half, and then one unit goes one way, the two other units go the other way. So that reinforces exactly what we would like to see. So VAST integration. The way we're currently doing VAST integration is through a file transfer method. So we're not training in VAST. We're still training in the OpenAI framework. But once we have a trained agent, we can make it talk to VAST fast enough where a human can play against it, but not fast enough where we're training in VAST with with VAST combat rules. So that is good in that we can verify that our agents are acting correctly, but it also has some limitations in it. So if we have to be careful when we're designing our our own mini wargaming combat engine within the OpenAI framework that we stick to as close to what VAST does as possible, because if we diverge away from VAST's rules and how it's adjudicating interactions between units, what will happen is the agent will start basing its combat decisions off of a wargaming engine that's not in use, and so we could get some very suboptimal behavior here. In this script, so what is happening is that the Python script on the back end is started, and then those instructions are passed along to VAST, and that's what all of these pre-scheduled movements register in VAST. So I'll play that again. You can see the blue units are starting to move. That is the computer moving them to close with and engage the enemy. So this was a very simple scenario, but just demonstrating that the agent is talking to the right units within the VAST framework and that it can move them, and it demonstrates at least some reasonable behaviors that we would like. So the big thing for us right now is results on way ahead. Where are we going with this thing? We would like to continue to see our agent demonstrate these basic principles of war and be integrated into a larger combat simulation. We really want to continue adding more and more terrain effects. We want to look at larger scenarios, and we're looking to increase the number of unit types. And so that's really the big test for this next year. Can we go to a brigade on brigade fight where each brigade is controlling multiple companies, where we have armor units and infantry units and artillery units? Can we add in a bunch of extra terrain? Do we still see reasonable behavior out of these agents? Do they learn optimal behavior? Because sometimes you can get reasonable behavior, but you can't get optimal. And so that'll be an interesting push for this next year as we keep trying to expand the scope of this particular project. We're also looking at moving beyond VAST to possibly some simulation engines rather than wargaming engines. And looking at how we can do that training within the actual simulation. But simulations, training in simulations requires a fair bit of infrastructure. So if you don't have any experience with reinforcement learning, one of the key takeaways is that you have to be able to interact with the simulation at a very basic level at every single time step, whatever you define that time step to be in. So the simulation has to be able to tell you what the state space is at that particular time. And then there has to be an available action space. And then you can inject those actions into the simulation. The simulation then runs through the next time step and processes the actions that have been selected. And so if you think of it like a board game, you have to pass not only the state of the board game, if you think of maybe a chessboard, the agent has to know what the chessboard looks like at every single snapshot, but it also has to know what its legal moves are. And so that is some of the complexity of doing this with actual military units, because not everything is a defined effect. So if we start talking about non-kinetic effects, that gets a little bit muddy. What are the effects of doing something like electronic warfare or something of that nature? And so that's kind of open for debate right now, but we're looking forward to coming up with some solutions for all of those challenges. Concludes the formal portion of my brief. I know that we have quite a bit more time lined up for this particular brief, so I'm happy to field questions if you all have them. If there's something you'd like to know more about, or yeah, I'm on all the y'all's time.
Thank you, sir. If anybody has any questions, feel free to just go ahead and ask your question.
So is the goal to eventually be able to simulate like whole actual day-long battles with this, or what?
Yeah, so the goal is to enhance our ability to look at more of the decision space within a simulation right now. So if you run a military simulation right now, you have to not only craft what that simulation looks like and the equipment available to all of those individual units, but for a lot of these simulations, you have to go through and plug in what are the reasonable behaviors for an agent within this particular construct. So, if TRAC is doing some sort of evaluation of some future technology, we have to say, how would this technology get used within the battlefield? It would be much more time efficient if we could have a reinforcement learning agent learn some of those lessons for us. So, if I give this reinforcement learning agent a cannon that can shoot 1,000 miles, which is an exaggeration, but how would it learn to employ that particular piece of technology? And because it can hopefully learn some of those things itself, that reduces the workload on the analysts. They can focus more on post-processing, focus more on analyzing results. Perhaps they can do a larger design of experiments that goes outside of the framework of the behaviors they originally defined. That's one of our challenges right now. If you try and do a design of experiments too large outside of these kind of known quantities, you're going to break the behaviors of the simulation. And so if it automatically adapted, that would be a huge gain for TRAC.
Okay, thank you. That makes more sense.
Any other questions?
Doesn't look like it. Well, thank you so much for your time today.
Okay, well, thank you very much. And if anybody has any questions afterwards, just send me an email, and happy to be in touch.
Thanks again.
Thank you. Really interesting.
Tomorrow, don't forget, we have our sessions, and we start tomorrow morning at 8 o'clock, if you're going to be joining those as well. And we also have a couple other sessions going on that you can still reach out in.
Thank you for your time. I really